Okay, we're going to talk about marginal distributions, and we're going to start out with an example to illustrate what this is before looking at the definition. So let's imagine here that we're given a joint PMF, so for discrete random variables, p of x, y, and those are variables x and y, and that is given to us in this table right here. And so let's just remember what a joint PMF is. The P of xy is the probability that x is x and y is little y. And so that little comma, remember, means and. It's like saying the probability that x is equal to x is one event and that y is equal to y. So we're given this table, which gives us the values. And let's imagine that we want to find these two values here. Let's say that we want to find the probability that x is 3 and the probability that x is 4. So how are we going to do this using this table? Well, we're going to apply the law of total probability. The law of total probability, which says if you have a partition, so we have to remember what a partition is. A partition divides the sample space without missing anything. So it includes everything. It includes everything, but also in a very specific way. It includes everything so that there is no overlap, so that we have events which are mutually exclusive or disjoint. And if we have that situation, then you can take the intersection, right? If you want the probability of x equals whatever, you take the intersection with each of the subcases in the partition. And so y equals 1 and y equals 2 is a partition. They cannot happen at the same time. They are mutually exclusive, and those are the only two values in the table. So they are exhaustive. They include everything. And so what we do is we take the value x is equal to 3 and y equals 1 and add to it when x equals 3 and y equals 2. That's the law of total probability from your previous probability course. So that is just a matter of plugging in p of 3, 1 and p of 3, 2. Reading those directly off the table, that's 0.01 plus 0.04 right here, and that gives me 0.15. And so we'll do the exact same thing. Do the exact same thing for p of x equals 4. Right? There's only two possibilities. X is 4 when y is 1, and x is 4 when y is 2. And so we add up those guys again, and we get 0.17 plus 0.18 is 0.35, right? So we're adding here. Now, I want us to notice that really what this amounts to is we've just added up a row. We've added up two rows, one for x equals 3 and one for x equals 4. And so we could do that for all the rows. And in fact, there's nothing special about rows. We could do that for all the columns. And so that's what I've gone and done here. I've added up each row and each column. So adding up the row of x equals 1 gives me the probability that x equals 1. Same thing with x equals 2 and x equals 3 and x equals 4. We'd done previously. Adding up those rows gave me probability for each value of x. Now we have to remember something, right? From a single variable PMF, the probability that x was equal to x, that is exactly what the PMF gave us. And if we have this for x equals 1, 2, 3, and 4, it's like I have the PMF for x. And so I can take that into a separate table, just like you would have had in your single variable probability course. The only thing is that we change the name a little bit since P was the name of the table, right? This was P of x, y. So as to not run into any confusion, we don't call this P of x, right? We call it P sub x of x to show that it is related to the original p, but it is for the variable x. And we put all those values into one table, and it looks like a regular PMF. And of course, there's nothing special about doing this with columns. If we add down the rows, so when y equals 1, there are 4 possibilities. They are mutually exclusive and disjoint, so we can add them all up, and we get the probability that y equals 1 turns out to be 0.5. Add up the second column when y equals 2, and you get, incidentally, the same value here. That also is a probability mass function, but to be clear that these are y values, we call this p sub y of y, and it is now a single variable probability mass function. So these functions, these single variable functions that are obtained, I don't want to say the word derived because they are not differentiated at all, but they are obtained. They are obtained from the joint distribution. They are called the marginal. They are called the marginal distributions of the jointly distributed variables x and y. So we have 2 marginals in this case because we have 2 variables, p sub x of x and p sub y of y are the marginal. They are the marginal distributions. And the name, where does the name marginal come from? Well, it comes from where we kind of wrote the sums. If you write the sums here, you're kind of writing them beside the table, or you're writing them in the margins, and that is really where that name comes from. That those marginal distributions are when you add up and write the totals in the margins. But it's important to point out that in economics, the word marginal with respect to a function means something else, right? So if you're talking about the marginal profit or the marginal cost, you are talking about the derivative of the profit function or of the cost function. That is not the case with our marginal distributions. They are not derivatives. They are not. So the word marginal means something quite different to an economist than it does to a statistician. So after that example, let's go ahead and look at the definitions, the formal definition of this. So the marginal probability mass function of x, denoted by p sub capital X of little x, is given by the sum over, and what does this mean? The sum over all y values. The sum over all y values, all of them. And if you're adding up over all y values, all that's left is x, right? And similarly, the marginal probability mass function of y is the sum over all x values for each possible y, and then you get those distributions that we had above. So a similar definition for the continuous case. In continuous cases, we're not adding up, we are integrating, and so here is the definition: the marginal probability density function, not mass, for a continuous random variable of x and y are denoted by f sub x of x and f sub y of y, right? So they are the marginal distributions of f sub xy, which is the joint density, function. And so what do? We integrate out the y. In fact, that is what people often say: integrate out y, which means we integrate over all possible y values from minus infinity to infinity, right? All possible y values. So we integrate over all possible y values, right? And if we do that, if we're integrating with respect to y, what is left when the y gets integrated out is a function of x. And so that function of x is, right, for whatever the support of x was to begin with. And the same thing here, if we do f sub y of y, we are integrating now over all possible x values, x from minus infinity to infinity. That is going to get rid of the x, and what will be left is a function of y over the support of the y variable. So those are the formal definitions of the marginal PMF and the marginal PDF of jointly distributed variables. Let's go ahead and look at an example for the continuous case. So let's say that we are given a joint density function for variables x and y, and it's given here as f of xy is 2x plus 4y over this region where 0 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to 1 minus x. So there is the support of x and y, and outside that region, there is zero probability density. We are being asked here to find f sub x of x and f sub y of y, which are these guys up here, the marginal density functions for x and y respectively. So we are going to apply these definitions. We're going to apply these definitions. So the first thing that we need to do to apply those definitions is figure out what this support looks like, because we are going to need to integrate over it. So let's draw that. If 0 is less than or equal to x is less than or equal to 1, and 0 is less than or equal to y is less than or equal to 1 minus x, then we have this region here where this is the line, y is 1 minus x. And so we have a triangle in the first quadrant, the triangle with the intercepts of 1 and 1. So there are the same inequalities above that gave us that were given to us in the density function. So we want to integrate out. The definition tells us to integrate over from minus infinity to infinity. Well, there's a whole lot of zeros in that, right? So that is like integrating over all possible y values. So y goes from 0 to 1 minus x. So from 0 to 1 minus x of the density, and the density was given as 2x plus 4y dy. That is just an integral that you will do using your anti-differentiation rules and the FTC, right? So antiderivative here with the same bounds, you plug in and you simplify, and you end up by getting this. There is the marginal density. There is the marginal density function of of x, right? It looks like a single variable, right? Well, it is. It's a single variable function. Now, we are also asked to find the density of y. So if we're finding the density of y, we need to integrate out the x, which means that we need to change this region. So like we did when we did our double integrals, we did type 1 and type 2. We need to re-express this region in terms of type 2 so that it can be integrated and remove the x. So we want to integrate with respect to x. So x in this region then will go from 0 to 1 minus y. So the minus infinity to infinity over the support becomes from 0 to 1 minus y of the density function 2x plus 4y dx. So we integrate, anti-differentiate, plug in the bounds, simplify, and we end up by getting this as the marginal density function of the y variable. So now that we have those, what can we do with them? Well, we can calculate probabilities just like we would in a single variable case. So let's find the probability that 1/4 is less than, or just less than y is less than 3/4. And we want to find that in two ways. There's actually three ways that we could do it. The first way, which is actually not part of the question, if I want y is 1/4, right? If I want 1/4 is less than y is less than 3/4, if I went back to my region, and I said 1/4 and 3/4 here, and I wanted y in that interval, right? If I wanted all the y's in that interval, well, that corresponds to part of the support. So I could actually do a double integral over this trapezoidal region here, a double integral over that trapezoidal region, right? So if I call that region D, how about that? If I call that region D, the first way would actually be a double integral over D of the density function, dA. That would give me this. It would actually, if you went and calculated it, you would notice that a lot of the steps that you were doing amount to steps that were done in the marginal functions. Okay, and so what we're being asked here in the two ways that we're being asked is not by using the original density function, but by using the marginal density function of y, and actually then using the CDF for y, So let's do these two ways, but there is this other possibility as well. So if we are going to be using the marginal density function, then we are integrating exactly as you would in a single variable case. So the probability that 1/4 is less than y is less than 3/4 is the integral from those bounds of the density. That's it. That's what you would have done in your first variable case. And so you do the exact same thing here with the marginal density. The marginal density acts exactly like a single variable density function for y. So you have, here was our marginal density, here are our bounds, integrate, plug in the bounds, and you get 19 over 32. So when we do the second way around, and we find the CDF for y, which is going to act exactly like the CDF would have in the single variable case. When you find the CDF for y, you can use it to calculate probabilities. And so the definition of the CDF here is the integral from -infinity to y value of the density function with some dummy variable t. And we know, right, by definition, this is the probability that y is less than or equal to that little value y. So this integral that we're going to do here, well, that integral is going to feel very familiar because, I mean, whether you do a double integral as up here, whether you do a marginal, which is up here, or whether you do the CDF first, you're going to have to integrate. There's no way around it unless you're given the CDF, unless you're given something which has already been integrated for you. So we're going to integrate from -infinity to y of the density function. Now I need to be careful. That density function is only equal to this on our triangular region, right? On our triangular region would look like this. Otherwise, it is 0. And so if I'm careful about where I'm integrating and that sort of thing, I will get 0 if y is less than or equal to 0, right, on this part here. I will get y plus y squared minus y cubed if y is between 0 and 1, and so on this part here. And that shouldn't come as any big surprise, right? That is the same value that we got above because it's the same density function that's being integrated. No great shock there. And then 1 if y is less than, greater than 1, right? So past the edge of the triangle on there, you have the complete density. So the CDF is now given to us completely here. And how do you use the CDF? Well, it is an antiderivative, and so you are just doing, right, you're doing this step, basically. The CDF takes care of this step. You are doing f of 3/4 minus f of 1/4, and you are going to get the same 19 over 32. In the next video, we are going to look at a use of marginal density functions, and that use will be to tell us whether the joint variables, the variables that we have jointly distributed, are independent or not.